Hello there, and welcome to our lecture today. Today we're going to talk about Chapter 10. Chapter 10 deals with molten atomic theory. In this chapter, we're going to talk about our friend the electron as it transitions from lower energy level all the way up to a higher energy level and perhaps back down again. What's left to say other than this is part 1 of Chapter 10. Go, electron, go! Part 1, Chapter 10. Okay, everybody, welcome here. It is Chapter 10 time. We're talking about modern atomic theory and the periodic table. Really, this chapter is going to be all about our friends, the electrons. So, really, pretty much that is what we're going to focus in on this chapter. We're going to talk about what happens when electrons get excited, when they move from one energy level to the next. We will also talk about electron configuration, how you write electron configuration, something known as orbital diagram. And I think we'll finish up the chapter talking a little bit about electron configuration, the periodic table, and also electron configuration for ions, so things that have charges, how that affects electron configuration. So let us get into sort of the idea of what we're talking about here. A reminder from what we talked about, excuse me, in a earlier chapter. Rutherford's atom, right, was basically found to be mostly empty space. Within that empty space was a very dense positive core, and that core was obviously our nucleus, as we talked about. And as we talked about in our nucleus there, right, we have our protons, which are positively charged, and our neutrons, which have no charge, right? So there are protons and our neutrons. And again, outside of the nucleus, in that sort of empty space, we do have electrons sort of traveling around the nucleus. And as we'll talk about in this chapter as well, they really do travel in a pretty random pattern. They don't travel in pretty orbits, which we'll talk about here in this chapter a little bit more. But one thing that we do know for sure is obviously the nucleus is very small compared to the size of the atom. So remember that those electrons in that empty space, although they are flying around and negatively charged, there is going to be some attraction between those negatively charged electrons and the positively charged really nucleus. And that's really what keeps certain electrons near the nucleus in certain energy levels. That's also why electrons maybe further away from the nucleus are not held as tightly. And as we'll talk about, I think coming up in the next chapter, in terms of bonding, that's really why certain electrons are involved in bonding, for example, and other ones are not. And there's kind of two different types of electrons. We'll get into a little bit here, I think, in this chapter, but we will definitely talk more about it in that bonding chapter. But also why electrons just don't kind of fly away, if you want to think about it that way. There is still that electrostatic attraction between the electrons in that empty space because they're negatively charged as they're flying around to that positively charged nucleus. So sort of the beginnings of the idea of what we're talking about here, which is electrons and sort of how electrons transition from one energy level to the next. So ultimately what we're kind of be looking at in this chapter is the idea that, you know, you have perhaps an electron represented by the arrow on a certain energy level. You know, maybe it finds itself going up to a higher energy level, and eventually though it will come back down to a lower energy level. So you know what we're talking about is sort of what happens also in terms of energy to allow those electrons to sort of transition to, say, a higher energy level and then come back down to a lower energy level. So a lot of work was done early on by a physicist named Planck. He actually has a constant, as we'll see later on, which is known as Planck's constant. He did a lot of experiments where he heated a lot of solids, and a lot of radiation was emitted as a result of that heating. And one of the things that sort of came out of Planck's work was this idea of energy being transferred and what is sometimes referred to as a quanta of energy, quantum of energy. And the idea of a quanta of energy is that energy basically will be sort of transformed and given off are absorbed in only definite amounts. So, for example, when we talk about this electron going from a lower energy level, for example, here to a higher energy level, this electron in the atom, for example, needs to actually gain energy, right? To do that. And remember that when something gains energy, that's an endothermic sort of situation. And as we talked about in the energy chapter, that's basically going to be a positive value for energy. Now, the opposite would be true if we had, say, that electron in the higher energy level, right, to start with, and it wants to come back down to a lower state of energy. And when it does so, what has to happen for that is, because that electron's in a higher state of energy, energy has to actually be given off in this situation. So you might be wondering sort of what is the idea sort of a quanta of energy, and we'll talk a little bit more about it as we continue on. But the idea is those electrons, for example, as they are transitioning from one energy level to next, either going, say, from a lower energy level to a higher energy level, or a higher energy level to a lower energy level, like on the right there, they will always gain or lose energy in these discrete amounts of energy, which means they will either gain enough energy to completely transition to one energy level or the next, or they will lose enough energy to completely transition to one energy level or the next. So the idea of sort of quantized energy, you could kind of think of it like stairs, for example. And when we think about it like stairs, the idea here is when we walk, say, stairs, we can go to this step, right? We then go perhaps to this step. We go to this step, right? We don't go, I'm just going to go past the first step. I'm just going to stop like right here in between steps, right? Because you would fall, right? So we usually will have enough energy to completely transition from, say, one step to the next. We never stop like halfway through on the steps because obviously you would fall. And that's sort of the same idea as we'll talk about in this chapter of how electrons transition from one energy level to the next as well. They have enough energy level to completely go from one energy level to the next energy level. Just like when somebody walks stairs, right? Maybe a person can do only one step at a time, but there are sometimes people that can kind of, have enough energy and reach to go 2 steps at a time. I don't know about 3 steps, 4 steps, but the same idea also happens with electrons as they're transitioning. Some electrons will gain enough energy to transition more than one energy level up. Maybe they go 2 energy levels, 3 energy levels, whatever it may be. And the same idea when they lose energy, they will lose energy the same way. They will lose energy enough to go 1 level, maybe down 2 levels, 3 levels, whatever it may be. So that's the idea of quantized of energy. We sort of think of it kind of like a staircase. There's these distinct stairs, right? Where if you're walking up or down a staircase, you're either going to find yourself on one step or the next, either higher on the staircase, kind of like higher in energy, or lower on the staircase, like lower in energy. Again, you will never find yourself between steps because you won't be able to stand there, right? You would fall. And that's the same idea as how electrons transfer. So this idea of quantized energy is very important in terms of modern atomic theory. And it led also to an understanding of radiation. And radiation is really the emission or transmission through space in the form of waves. And waves is basically how energy is sort of transmitted through space. So, for example, as our electron decides to come back down to a lower state of energy, it has to give off that energy, and it gives off that energy in the form of a wave, which is sometimes referred to as a photon of light. And the idea also goes back to that important law that we talked about, which is the law of conservation of energy. We don't lose energy or gain energy along the way. So as that electron has to lose the energy, the atom has to emit that energy, and again emits it in the form of a wave. This is essentially, for example, how like fireworks, for example, work, right? In fireworks, there is a lot of different elements, and when they launch them, they explode, right? There's an explosion, which provides a lot of energy. So all those elements within the fireworks, those electrons get really excited. And as they start transitioning, for example, back down to say a lower state of energy, it will give off light in the, as we'll talk about, visible part of the spectrum where we see color. And we see the colors that kind of in the sky, red, green, blue, wherever it may be. And that's a result, again, of sort of this energy being given off as a result of the fireworks in the form of waves, and in the form of a wave in the visible part of the spectrum where we actually can see colors. So that's sort of a real life sort of application of sort of what's happening here. Now let's talk a little bit more about a wave. A wave is basically a vibrating disturbance, which energy is transferred. So we have our bird having a good day there at the beach. And as he sits there, the wave's actually passing him, right? He's actually not moving. The wave is moving past him. Speaking of waves and energy, right? It also provides a certain amount of energy. Those waves are associated with them. So if you just think logically, if you ever were in the ocean, right, and you got hit by a wave, some of them are pretty powerful, right? They have a certain amount of energy associated with them. And the same idea here, as that wave is given off by the atom of a photon of light, it does perhaps correspond to a certain, say, color. And it may not always correspond to a color. It may come off somewhere else and you may not see a color, but it also will have some type of energy associated with it. So let's talk about some of the different parts of a wave, just to make sure everybody understands that. So when we look at a wave, prettier picture coming up, I think, on the next slide, but we got a wave kind of happen like that. The wavelength, which is lambda, is from one peak to one peak, or sometimes referred to as a trough to a trough, which is the lower guy. So this is our wavelength here. Wavelength is the distance between identical points. Common units of wavelengths are meters, centimeters, and nanometers. And I would say in most cases, if you had to do some type of calculation, meters is usually where you want to get your sort of wavelength to. Reminder that centi, right, are centimeters. There's basically 100 centimeters in 1 meter. Also, nano, right, is our 10 to the minus 9. So in 1 nanometer, there would be 10 to the minus 9 meters. So those are some common conversions that are sometimes used if you do have to do a calculation involving waves, wavelength, and things of that nature. To be truthfully honest with you, in this class, we probably won't be doing many of those calculations, if any. I may show you some as we go through this chapter, but just to show you sort of how those equations would work in a calculation, I don't think we'll be doing too much of those calculations here. Frequency is the number of waves that pass through a particular point in 1 second. Usually the units of frequency is a hertz or a reciprocal second. And 1 hertz is equal to 1 reciprocal second. So they are the same. The units are the same. By the way, this is sometimes people call it a V, but it's not. It's kind of a fancy V, which is actually, that's what nu is. It's sort of the actual name of it. So the little fancy V there, which is the nu, is actually the symbol for frequency, just like lambda here is the symbol for wavelength. The amplitude is from the midline to the peak of the wave. That's the amplitude, basically. And we can calculate the speed of the wave, which is sometimes abbreviated with the U. Is the wavelength times the frequency. So if we just look at the units here for like a speed of a wave, wavelength is usually in meters. Frequency is usually in reciprocal seconds, which is to the minus 1. That's basically meters times 1 over seconds, which is reciprocal seconds. So typically, if we calculate the speed of a wave, It is usually in units of meters per second when we multiply them together. So that's a very common sort of unit of a wave. So here's a prettier picture of a wave. And again, we see our wavelength. Our frequency is really, by the way, when we talk about our frequency, it's, how often the wave passes a particular point in a second. So that is the frequency. Now, there is sort of a relationship, by the way, between the wavelength, energy, and frequency. So in general, if you have a wave that has a pretty long wavelength, like something like this. So typically waves that have long wavelengths will usually have a lower frequency. And usually that results in, say, lower energy. Like, for example, the color red. Red has a longer wavelength than, say, we'll go with purple, which is what we see in this one. So purple, for example, may have a much smaller wavelength. So it has a smaller wavelength. That means it usually will have a higher frequency. And usually that would result in higher energy. So the wavelength, the frequency does play an effect in terms of the energy associated with that. And as you can see here on my example, even colors. So when energy is given off in the form of a wave that falls in the visible part of the spectrum, and we see different colors, when you see red versus yellow versus blue, green, purple, colors, right, is like our Roy G. Biv, right? Red, orange, yellow, green, blue, indigo, and violet. Those are the different colors that we see. Even between colors, there's a difference in terms of energy associated with those waves. For example, again, the red has a much longer wavelength than, say, purple, and thus red is actually lower in energy than, say, a purple one. What does that mean? As we'll talk about, there is some importance to that sort of distinction as well. It also can give you an idea as to how far perhaps electrons are transitioning, how many energy levels they may be covering in terms of what color that you may see come off. So the idea here, as we go through electromagnetic radiation, is the idea that light behaves like electromagnetic radiation, which is that emission of energy in the form of waves. Electromagnetic radiation can sometimes have properties that are characteristics of particles. And a lot of what was sort of discovered, including by like Einstein through some of the photoelectric effect as well, was this idea of sort of the dual nature of light, and the idea that light can have both wave and particle-like properties. So particles can behave like particles, but also in certain instances can have functions that behave much like a wave would behave. And waves can also obviously function like waves, but also have some particle-like characteristics. So there's just kind of dual nature of both light, waves, and particles in this idea of what we're talking about here. So we can think of a beam of light that's traveling through space as really these tiny packets of energy, which are referred to as photons. As I mentioned before, the longer the wavelength of light, the lower the energy and also the lower the frequency there is. The shorter the wavelength of light, we have a much higher frequency and a much higher energy associated with it. So this is sort of the dual nature of light. We could think of it as having, again, characteristics that are very much like waves, like we see on the top there. But we could also think of it as packets of energy, which is more like particle type of information and characteristics. Here's an example of that. So this is even looking at the color red versus the color blue. Here we see red once again has a much longer wavelength than in comparison here to blue. So what we see is, for example, Red would be lower in energy than blue. What does that mean in terms of relationship to electrons being transferred from one energy level to the next? Well, if you think about just realistically here, just if these lines represent some different energy levels, say 3 different energy levels, and energy increasing as you go upwards. So let's just say we had an electron at the very top here, and it decided to transfer all the way down to the first energy level here. Once again, in order to do that, it's going to have to give off a wavelength of light or a photon to release that energy to allow it to go from a higher energy level to the next. That's a lot of transitioning. That's a lot of energy levels. That's probably a lot of energy associated with it. Perhaps what would happen in that case is you would see, if it was part of the visible part of the spectrum, maybe the blue light coming off, because that's associated with a lot more energy, as opposed to maybe you had an electron that was, say, at this energy level, and it just kind of transitioned down one energy level. Not as much of an energy change, but still going to give off that energy in the form of a photon of light. But because overall not a tremendous amount of energy changed, maybe you will see coming off something more like red in color if it was part of the visible spectrum. So, depending on the colors that you might see coming off as these electrons transition, you can make a fairly educated guess as to how much energy is associated with it. Is it a large amount of energy change or a small amount of energy change? And perhaps what colors you might expect to kind of see. So a feature of all electromagnetic waves is the speed at which they travel, and that's 3 times 10 to the 8 meters per second. That is the speed of light, which is what c is here. So c is the speed of light. And when we deal with electromagnetic radiation, we actually use this formula here. C is equal to the wavelength times the frequency. Once again, the speed of light's in meters per second. That means when you use this equation, it does have to be in meters, and the frequency does have to be in reciprocal seconds to obviously give you meters per second there on both sides. If I wanted to know the wavelength and I do know the frequency, I could take c divided by the frequency. If I want to know the frequency and I know the wavelength, I could take c divided by the wavelength. Once again, c is a constant, which you always sort of have available to you. So if you know one of those two things, either the frequency or the wavelength of light that's coming off, again, perhaps as electrons are transitioning, you can very easily figure out either what the wavelength was or the frequency, depending on the information given to you. So again, just to kind of show you how you would do that, here in an example, we have the frequency. We want to know what is the frequency of a wave that has a wavelength of 4.68 times 10 to the minus 7 meters. So we're looking for the frequency. We have the wavelength, which is 4.68 times 10 to the minus 7 meters. There we go. Once again, here we could use c is equal to the wavelength times the frequency. Here we would solve for the frequency by dividing the wavelength to the other side. Remember that not given to you a lot of times, but you always have the speed of light, which is 3 times 10 to the 8 meters per second. Some books will use 2.997, something like that, times 10 to the 8. I personally use 3 times 10 to the 8, and a lot of people will use that as the speed of light. Now, again, we want to look at units. Our wavelength is in meters, so is that. So that's all good to go. So we basically would just put it in here, 3 times 10 to the 8 meters per second, divided by 4.68 times 10 to the minus 7 meters. Once again, meters on top and bottom will cancel. And I will find me a calculator here. All right, well, let's get a find a calculator. I suppose that would be helpful to have one. So let's go with 3 to the 8. Make sure you use your exponent button. So 3 exponent button 8 divided by 4.68 exponent button negative button and 7. And that's going to give us a frequency here of 6.41 times 10 to the 14. The units here are actually 1/seconds. Or you could write reciprocal seconds, whichever way you want to kind of do it. And that would be our frequency associated with this wave that comes off. Now, if we look at another one here, In this case, we actually were given the frequency, and we want to know what is the wavelength in nanometers. So just again, to show you how you could use these formulas here, we're looking for the wavelength in nanometers. We do have the frequency given to us at 5.6 times 10 to the 14 hertz. A reminder that a hertz is the same as a reciprocal second. It is a 1-to-1 relationship, which means that this frequency is really 5.6 times 10 to the 14 reciprocal seconds. At this point, again, we could use our C is equal to our wavelength times our frequency. In this case, we're going to solve for wavelength, so we're going to divide our frequency to the other side. And when we do that, we will get that the wavelength is equal to C divided by the frequency. Once again, here we're good because we do have the speed of light, which is 3 times 10 to the 8 meters per second. Obviously, our frequency is in reciprocal seconds, so the seconds will actually cancel out here. So these guys will cancel. Remember that that's 1 over seconds on the bottom. When you divide it, the seconds come to the top and they actually cancel. Once again, we want to make sure that we do use our exponent button here. So 3 to the 8 divided by 5.6 to the 14. That is going to give us 5.36 times 10, a lot of zeros there. 1, 2, 3, 4, 5, 6, 7, minus 7. And these would be units of meters. We do want nanometers, and a reminder, nano is 10 to the minus 9. So that means in 1 nanometer, there are 10 to the minus 9 meters. So here we will divide out 10 to the minus 9 meters on the bottom, 1 nanometer. By the way, 10 to the minus 9 is the same as 1 times 10 to the minus 9. If you need to punch that into your calculator that way, we will then divide what we got there by 1 times 10 to the minus 9. And that's going to give us 536 nanometers in this case. It should be somewhere in that visible part of the spectrum, I think. So this is how you can use those equations, because you always have the speed of light as a constant. That number always available to you. If you know either the wavelength or the frequency, like in these two problems, you can easily calculate the other frequency or wavelength depending on which one is given to you. This is the electromagnetic spectrum, and talk a little bit about this. This is what is known as the electromagnetic spectrum. And you do need to be familiar with the electromagnetic spectrum. You don't really need to know exactly off the top of your head for quizzes and exams where each of these parts break off at in terms of the exact wavelengths, but we'll talk about what you do need to know. So here's the wavelength up on top. So this is the wavelengths. And we have 10 to the 4 on the right-hand side here. We have 10 to the minus 12 on the left-hand side. So clearly on this side, that is a much longer wavelength. And what we know about that is what we've been talking about. Because that's a longer wavelength, that means we will have a lower frequency, and that will be lower in energy. On the other side, this is a much smaller wavelength, which we know that translates into a higher frequency and also higher in energy as well. So let's talk about this. So on the sort of lower end here of energy and longer wavelength, we have things like radio waves, like AM, FM type of things that you listen to in your car. By the way, when you dial in, just so you know, right, your radio to a specific station, say like 95.5, that's actually 95.5 megahertz. That's the frequency you're actually dialing in to that. And obviously there's a certain amount of wavelength that's associated with that radio wave that comes out. Also energy associated with that. If you kind of go to the left here, we're getting a little bit smaller of a wavelength. So that means that we are increasing energy as we go to the left. And we get something like microwaves. And microwaves, for example, have enough energy to like spin water molecules really, really fast. So when you cook your pizza, it's like done in 3 minutes, which is not bad, I suppose. So a lot more energy than, say, radio waves. Going to the left even more here, we're going to hit infrared part of the spectrum, or the IR is sometimes referred to. And the infrared part of the spectrum, which again is sometimes referred to as the IR, has a lot more energy than microwaves. And again, because we're now getting into a smaller wavelength, we're going from like 10 to the minus 2 meters to 10 to the minus 4. And as we go next door, we hit the visible part of the spectrum. The visible part of the spectrum is the part of the spectrum where we see colors. That's what I said earlier. That's our ROI, right? Red, orange, yellow, G, green, BIV, blue, indigo, violet, right? That's our ROI, G, BIV. And those are where we see color come off. And as we talked about as well, even within colors here, there are differences in terms of energy associated with that. Again, as we saw in a couple of those examples, red having the longer wavelength, going to be lower in energy than, say, violet or blue, as we saw there, which will have a shorter wavelength and will have higher energy. So even between colors, we will see a difference in terms of energy. So in order for us to see a actual color come off, the energy as those electrons, for example, are transitioning, like say in fireworks, or if you have done a flame test or looked at an electric discharge tube lamp, like a neon lamp, we see color. And we see color because the wavelengths that are coming off are falling in this visible part of the spectrum, and that's associated with a specific color. Next to it, in terms of the spectrum here, is the ultraviolet or UV part of the spectrum. And the UV part of the spectrum, that's sometimes referred to as the vis part of the spectrum. The UV part of the spectrum is ultraviolet, and that is obviously smaller wavelength, more energy. That's also why we throw sunblock on, right, when we go outside, because ultraviolet light, right, is outside, and it has a lot of energy associated with it. So we use it to sort of block, hopefully, some of those rays, and we don't get too sunburnt or anything like that. Going to the left, even smaller wavelength are X-rays, which is probably why when you take an X-ray, right, they throw a lead vest on you and they leave the room when they shoot the X-ray, because it's obviously very high in energy. And lastly here, we have gamma rays, which is what we talked about when we were talking about sort of Rutherford's experiments earlier on in that chapter. But gamma rays are radioactive rays that have no charge. They're like pure energy. They're very, very high in energy. So this is the electromagnetic spectrum. You do need to know the electromagnetic spectrum. Once again, like I said, you do not need to know it in terms of exactly where everybody sort of breaks off in terms of their wavelength. But if you were given, like, you know, microwaves, infrared, UV, you know, gamma, and ask a question like, put these in order from highest energy to lowest energy, longest wavelength to shortest wavelength, highest frequency to lowest frequency, you need to be able to do that. So not specific in terms of the wavelength where all these things are found, but you do need to know sort of the order or how they are on the spectrum, and the order in terms of energy, frequency, and wavelength. That also goes for, you need to know the colors as well in the visible part of the spectrum, the same way in terms of higher energy, lower energy, higher frequency, lower frequency, longer wavelength, and shorter wavelength. All right, so atoms, as we've been talking about, can emit or absorb energy in these discrete quantities, which are, again, a quantum of energy. And that's sort of what we've been talking about in terms of like that staircase approach, where, again, these electrons are going to either gain or lose energy enough to fully transition from one energy level to the next. They again will not find themselves sort of in between energy levels or anything like that. Also, when we talk about absorb or emission, when an electron transfers from a lower energy to a higher energy level, that is an absorption. It has to absorb energy, as we've been talking about. So that's sometimes referred to as an absorption. And vice versa, as the electron goes from a higher energy back down to a lower energy, it has to emit energy. And again, that was sort of what we were talking about when we were talking about exothermic and endothermic. It's sometimes referred to as like an absorption emission. Absorption spectrum, as we'll talk about, and an emission spectrum, as we will see shortly. Now, speaking of energy, in addition to figuring out the wavelength or the frequency, if you know one of those two things, you can actually figure out the energy associated with a wave as well through this equation here, which is E, which is energy, is equal to H times the frequency. H is Planck's constant, which is this guy right here. 6.63 times 10 to the minus 34 joules times seconds. So those are the units. Joules, right, is a unit of energy. So in terms of our units of this guy will end up being joules. H is joules times seconds. And remember, frequency is reciprocal seconds, which is 1 over second. So seconds will cancel. And that is how we end up with joules in this case. Now, if we take the equation that we saw earlier, which is C is equal to the wavelength times the frequency, and since the frequency is in this one, we could solve for frequency, which is C divided by wavelength, and we could actually substitute that in to our frequency here, and we sometimes will get another version of this equation, which is E is equal to H times the frequency, which is also equal to HC divided by the wavelength. Now, this is helpful for a couple of reasons, because this allows you, once again, to know the energy associated with that wave if you know the frequency. But let's say you don't know the frequency, but you know the wavelength. This will then allow you to figure out the energy associated with that wave by just the wavelength. The reason for that is H is a constant, which you always have. And C, which is still our speed of light that we used previously, which is also a constant. So this gives you the ability, if you know, once again, the wavelength or the frequency of a wave, you can actually figure out the energy that's associated with it. So those two equations are oftentimes used together in that aspect. And if we take a look at one here together, just to show how that would work, we're looking for the energy. We do have the wavelength, which is 465 nanometers. So we have our equation, which is equals H times the frequency. This part of the equation, or this version of the equation, will not do us so good because we don't have the frequency. But once again, if we tie in our previous equation and divide it over, our frequency equals C divided by the wavelength. Now we can substitute that in. And that will give us E is equal to HC divided by the wavelength. We do have to be careful, though. Our wavelength here is in nanometers. Remember that C is 3 times 10 to the 8 meters per second. So those units are not going to cancel out correctly. So we do have to calculate it. And once again, H, which is Planck's constant, is a constant that we just saw in the previous slide, which is this number here, 6.63 times 10 to the minus 34 joules times seconds. So putting these numbers in, our energy is equal to 6.63 times 10 to the minus 34 joules times seconds, are 3 times 10 to the 8 meters per second, and all going to be divided by our wavelength that we do need to convert. Once again, nano is 10 to the minus 9. So doing that conversion there, 465 nanometers. And once again, that means that 1 nanometer is 10 to the minus 9 meters. So grabbing my calculator here, 465 times 10 to the minus 9, going to give us 4.65 times 10 to the minus 7 meters. And that is the units that we need for this to work correctly. Meters on top and bottom will cancel. Seconds on the bottom and top will cancel. That's going to leave us only joules left over. So clearly, once again, make sure you use our exponent button. 6.63 to the minus 34 times 3 to the 8 divided by 4.65 to the minus 7. That's going to give us an energy of 4.28 times 10 to the minus 19 joules. So in this particular case, we only have the wavelengths given to us, but by able to use these equations here, we can figure out the energy associated with those wavelengths. Once again, just a reminder, I was kind of just showing you how we would use those equations in problems. I don't think for this particular class that we're going to do much of those calculations. You might maybe in lab or something, maybe do some of that, but in your next class, you might use these equations for sure. So you do need to know the equations in the sense of sort of what they are. I do not think too much that we're going to do these type of calculations or a lot of these calculations, if any, in this particular class. Okay. So then let's talk about an important sort of theory of the atom that was brought to us by Bohr. And Bohr's model, our theory of the hydrogen atom, goes back to the idea of theory, and theories, as we talked about, can be found not to be correct in all aspects of it. And this is really true for Bohr's model of the atom. His model of the atom, as we will talk about, works really well for what happens with hydrogen. Does not hold up all that well as you move away from hydrogen, atoms that have more electrons than hydrogen. Before we get a little bit more into his sort of theory, let's talk a little bit about some spectrum and an emission spectrum. And an emission spectrum is, as we were talking about, what happens as electrons transition from typically a higher energy level to a lower energy level, again going to give off that energy in the form of a photon of light. And once again, perhaps it hits the visible part of the spectrum, and we may see some colors coming off as a result of that. Now, an emission spectrum can either be continuous or a line spectrum, and it is kind of what the names imply. A line spectrum is very similar to what we see here. You get very distinct lines that come off at specific wavelengths as these electrons are transitioning. A continuous spectrum is again like everybody coming off at once. So we think of a like line spectrum as being, again, more quantized version, and that sort of staircase example where we're either on this energy level, or this energy level. You can think more of a continuous sort of spectrum of what's happening as sort of unlike a staircase. If you were walking up, not a staircase, but you found like a ramp or something, and you're just going to walk up this ramp, you basically can stop anywhere you like along the way, right? On the ramp, you're not going to fall or anything like that. So you basically hit all the way along the way, kind of a continuous sort of energy and things coming off all at once, like the sun, for example, will kind of do that. Elements and atoms will kind of do this more quantized version, the specific line where we're either here, there, or up here as they're going up or down. How do we get an emission spectrum? There's several different ways you can do that, but basically you have to energize your sample. You could do that, for example, it's simply like a flame test. When you put it into a flame, it gains a lot of energy. Electrons start to go crazy as they gain energy. They go up to higher energy levels. They come back down. Electrical discharge too, for example, which you might do in lab. I think you throw the switch, electrical current, kind of like a neon bulb or something like that. You'll see the color in the neon bulb come off, and you'll also have some electrons transitioning as is being energized through the electricity through the switch that you turn on there. So when we look at something, for example, like a iron bar that's removed from a high temperature source, it will really glow, and that's the visible part of the spectrum that we could see. We could also feel some warmth coming off of it. And that's a different part of the emission spectrum. That's the infrared. So it's also important to remember, sometimes people think that, all electrons that transition, for example, will always result in a color that you can see in the visible part of the spectrum. And that's not always the case. It does depend on the energy that's coming off and also the wavelength that's coming off. So perhaps some electrons will transition, and the result of that transition will be a wavelength that falls more in the infrared part of the spectrum, where you won't see any color associated with it. Maybe it does fall in the visible part of the spectrum where you do see color. Maybe it falls in the UV part of the spectrum where, again, you wouldn't see perhaps color in that. So again, not all transitions will result in things coming off specifically in the visible part of the spectrum. You can have electrons transitioning that will give off wavelengths in the different part of the spectrum. And again, it's not always going to be like a color. A common feature to emission spectrum of the sun and heated solids is this continuous. We get wavelengths of light are represented in the spectra. All wavelengths of light are sort of coming off at once. So if you look at something through like a spectroscope or a prism, which you might also do in lab as well, if you look at something that was illuminated, say, by sunlight, you shouldn't look directly at the sunlight, obviously, or the sun, but something that's sort of illuminated with sun, if you kind of look at it through a prism, it will separate the lights and you'll see all wavelengths kind of coming off at once. If you look at something like you also do, I think in lab as well, and you look at, say, an element that's being energized through electron discharge tube, like when you throw the switch on the little neon light, and you look at it through this sort of spectroscope prism type thing, it will separate out the light and you'll see these more distinct lines that come off. So not like the sort of everything coming off at once, distinct lines as specific wavelengths coming off. And that's, again, the difference between how the energy and the electrons are being gained and lost. These sort of specific lines that we see, which is what we do see for atoms in the gas phase, we see this line spectrum. And that's a result of what we've been talking about of, I have an electron on this energy level, it drops down to this energy level, it has lost the exact amount of energy to do that. By the way, that is represented by that equation that we saw there, E equals H times V, and it will lose that certain amount of energy, and it will correspond to a specific color line that we see, say, in the visible part of the spectrum. Every element has such a unique line spectrum that you actually can identify. For example, if you have an unknown, you can identify what unknown atom or element that you're dealing with based on the colors of the lines that you see, the wavelengths that they come off at. So for example, hydrogen here, which is what we're looking at, this is the line spectrum for hydrogen, and we see distinct colors coming off. So this is what you would see if you looked at it through that spectroscope, which a lot of times is a very badly drawn probably thing like I'm going to do here. Sort of a little box that you kind of hold. You look at it through here with your eye. Usually you'll have some type of little slit that you put at the eye source, and inside it will have this sort of rulerish type thing, and inside what you'll see is it will look something like that, and you will see these colors coming off at the specific wavelength, and that's why it's called a line spectrum. You see specific ones, and the idea of the line spectrum is the idea of a quanta of energy. Again, these electrons are transitioning completely from one energy level to the next. They're not stopping along the way. They're making a full journey from one energy level to the next, and the result of that is these distinct lines. Like this line here represents an electron that fully transitioned from one energy level to the next. This one, the next, this one, another one, and another one. Now, we also can see that obviously I got blue here versus orange. This is going to be lower in energy, right? The orange color, and this is going to be higher in energy, as we were talking about. So we can make a pretty good prediction, perhaps, that, you know, this orange color that we see here, or this orange line that we see here, is probably a result of an electron transitioning not a lot of energy levels, as opposed to, say, the blue one that we got there, or even the purplish one or violet one there at the very end. those guys are going to probably be a result of an electron transition, a much greater sort of journey, if you will. So again, if you had something like this, perhaps that transition of that electron all the way down to there would be a result of this line that you see, as opposed to, again, this electron just maybe transitioning down from the second one to the first one. That's maybe the orange line that we see. So again, that sort of difference of energy that we see and the amount of energy as they transition is important for, where we might see these colors come off. So let's talk a little bit about Bohr's model of the atom here. Bohr had this theoretical explanation of those lines that we just saw. It's really very complex sort of theory. We're not going to go into great details of it, but as I mentioned before, it really does sort of describe nicely what we see with hydrogen. But as it was later found, it doesn't hold up very well as we do sort of transition away from hydrogen to other elements. So Bohr's model is sometimes referred to as the planetary model, where we have electrons and we have our nucleus, right, where we have our protons and neutrons, and we have these orbits, which is sometimes referred to as a planetary model. And we have these electrons that are circling around the nucleus in these really well-defined orbits. And it's traveling in this sort of circular path where you can kind of put your finger out and, eventually along the way, the electron will basically come back around the corner there, if you will. Works really well to describe sort of what we're seeing there with hydrogen. And what he was talking about was electron is sort of restricted to a specific energy level or orbital. And as it transitions from one orbital to the next, that is where we see those colors, like the red line that comes up, the purple line that comes up, the orange line that comes up. These are energy levels, and he called this, for example, the n equals 1, n equals 2, n equals 3, and so forth. N equals 1 is the principal quantum number, is what n refers to. There's actually 4 quantum numbers that you'll learn in the next class, but the principal quantum number is what n is. And that's a fancy way of saying basically the energy level. And n equals 1 is really the ground state. It is, as we'll talk about here in just a second, it is the closest to the nucleus. Anything above that, like n equals 2 through 7, those are sometimes referred to as excited states. They are higher in energy. They are further away from the nucleus. So Bohr's model is these electrons that are transitioning from one energy level to the next. They are electrons traveling these nice, pretty orbits. They're restricted to one orbit or another, and they can only transition completely from one orbit to another. Again, we won't have an electron just transitioning in the middle here. It won't be there. It's got to either be in this orbit, this orbit, this orbit, whatever orbit there is. It cannot find itself sort of in the middle of any. Okay, so again, n equals 1 is our ground state here, closest to the nucleus, lowest in energy. N equals 2 through 7, any of those sort of orbitals further away are referred to as being excited states, higher in energy. So again, Bohr's model here, these electrons transitioning from one energy level to the next, they won't find themselves in the middle. They are moving these nice, pretty little circles, and as we'll shortly talk about, not really the case either. And then really, again, all of those lines that we saw as a result of those electrons transitioning. So here, for example, again, we see an electron maybe going from an excited state all the way down to the ground state, and that would be n equals 1, for example. And again, that's a longer transition, more energy involved as we go from more energy levels down than, say, our red guy here that's only making that one quick transition, resulting in the different colors that we see. And again, these different colors have different wavelengths and obviously different energy associated with them. So the principal quantum number, as I mentioned, is n, and as I said before, there really is four quantum numbers. N, which is the principal quantum number, is really, you could think about it as the energy level. And again, n equals 1 is referred to as the ground state or the ground level. It is closest to the nucleus, it's the lowest in energy. Remember that in chemistry, right, things like to be in a low state of energy or the lowest possible state of energy. And a lot of what happens in chemistry is that the point of trying to just get everything to the best possible state of energy, lowest possible state of energy, to make things as stable as possible. Again, these excited states, n equals 2, 3, and so forth, higher in energy, further away from the nucleus. And there's our transition that we talked about. So let's talk a little bit about the wave mechanical model and this idea of this dual nature of light. Another really important idea, and some of these things are leading us away from sort of Bohr's model, the atom, this planetary model. And one of these things was done by a guy named de Broglie. De Broglie actually reasoned through mathematics and stuff. He actually didn't do any type of actual experimentation, but through later experimentation, it was sort of proven to be correct. He reasoned that light rays could behave like a stream of particles and photons. Then perhaps particles like electrons could also have wave-like functions. And according to Broglie, an electron is bound to the nucleus and behaves like a standing wave, like a guitar string, for example, right? So the idea here is if you have a guitar string, you pluck the string, it's a standing wave, right? That wave can't go anywhere because, frankly, it's attached to the guitar. And it does create this wave as you pluck the string. It does have areas that are referred to as nodes, which have no amplitude. These are sometimes referred to as nodes, no amplitude. And that's sort of the idea that he reasoned with these electrons that, hey, you know, we have this positive nucleus, we have these negatively charged electrons, you know, they're sort of tied to them in the sense like a standing wave. So they can move around and stuff like that. And that's why, again, electrons just don't kind of jump off, right? All of them just don't leave. There's that attractive force that kind of holds them there, like your guitar string that's held to the guitar, but they still have some wave-like functions. So those points where we have no amplitude, which are known as nodes, just like we see with a guitar string that's plucked, we also have those in waves. So he reasoned that and concluded that waves can behave like particles, and particles like electrons, for example, can have a wave-like property. So this was a kind of a first step towards moving away from the idea of electrons traveling in these nice, pretty orbits. And like I said before, very predictable that you know, if I put my finger there, eventually the electron will come back around the turn. Another important sort of discovery and work that was done that kind of helped us move away from Bohr's model of the atom and how electrons are moving in the atom was done by Heisenberg and was sometimes referred to as the Heisenberg uncertainty principle. And the idea of the Heisenberg uncertainty principle is that it's impossible to know simultaneously both the momentum and the position of a particle with any type of certainty. The uncertainty part of it is this: the more information you have about how a particle, say like an electron, is moving, the less you know about its actual position, and vice versa. The more you know about sort of where a particle like an electron is located, the less you know about how it's actually moving. So these two things were really important for us to start to think about maybe Bohr's model here of how the electrons are traveling around in these pretty orbits is not so correct in all aspects of it. Further, it was this idea done by Schrodinger, who has a bunch of equations. And if you ever take physical chemistry, you'll deal with all those equations and stuff like that. But the idea of Schrodinger's equation, along with Heisenberg and de Broglie, led to this idea of, you know what, we do have to move away from Bohr's idea of I have orbits, I have an electron, they're traveling nice and pretty circles, to this idea of we really don't know how an electron is traveling around the nucleus. We don't know exactly where an electron is at a particular point in time. The best that we could do is say there's a very high probability, for example, of finding an electron in a particular part of the atom. With that being said, we still really do not know where it's at exactly, how it's traveling, how it got there. But we just know that, probability speaking, there's a really good chance that you could find an electron in a particular moment. So to sort of distinguish between the quantum mechanical's description and Bohr's model, we do move away from the idea that electrons are in orbits to this idea that electrons are in what are referred to as atomic orbitals. And atomic orbitals are essentially electron density maps. And they're theoretical sort of descriptions of where in an atom there's a really good high probability of finding an electron. So if we just think about logically, if we have our nucleus, which is positively charged, there's probably a fairly good probability that somewhere near the nucleus, you're going to find an electron. And there's also probably a less of a probability, if we kind of go way out here, of finding an electron. Not to say you could not find an electron way out there, but there's probably a much lower probability way out there than, say, down here in terms of where you would find electrons. So atomic orbitals are where we think about electrons are housed in an atom. And within an atom, we'll talk about each of these individually. There are s orbitals, there are p orbitals, there are d orbitals, and there are f orbitals. And these, again, are these probability maps and locations of where we could find electrons within an atom. Now, any atomic orbital, I cross it out, I meant to box it, but we'll kind of box cross. Any atomic orbital, it was found basically to hold a maximum of 2 electrons. So any individual atomic orbital could hold a maximum of 2 electrons. So if we look at sort of this electron density map, and that's what this is, we could see that if you think about the nucleus being right there in the center, you can see it's much darker, right? And that's a higher probability of finding electrons in this area. As you sort of fan out from that nucleus, you can see it's getting lighter and lighter, not as many sort of dark areas, and that's a lower probability of finding an electron in those areas. So we are moving away from Bohr's model of the atom and this orbit theory to an orbital theory where, again, we really don't know how electrons are traveling. We know they're in this empty space, they're traveling pretty randomly, and really the best that we could do is, I think there's a high probability of, hey, we could perhaps find an electron somewhere in this area, or there's a really good chance of finding an electron in that area. Once again, although there's a very high probability or a good chance of finding electrons in that area, I still don't really know where it is exactly and how it's moving, how it got there, just that there might be a fairly good chance of finding it. Here's another sort of density map. And again, you can see kind of the darker areas of the blue, a little higher probability of finding those electrons. And again, as you sort of fan out from the center there where the nucleus would be, it gets lighter and lighter. Again, not that you can't find an electron there, not that an electron is not going to be there, but again, there's probably a lower probability of finding an electron in that area. So let's talk about these atomic orbitals. And as I mentioned before, any atomic orbital by itself can hold 2 electrons. And let's take a look at what each of these are. So the first type of atomic orbital is, I kind of threw my picture on top of it, which is not so good, but this is an S, and it does say orbital behind it. So I'll just write here, these are S orbitals. So when we go to the first energy level, which is at n equals 1, that's the lowest state of energy, the only thing that we will find there is an S orbital, and is what is referred to as a 1s orbital. 1 meaning that it's on the first energy level, S meaning the type of orbital is. S orbitals start on the n equals 1 level. And they're on every other level after that. If you go to n equals 2, you'll have a 2s orbital. Still an s orbital. The 2 means it's on the second energy level. If you go to the third energy level, you'll find a 3s orbital. Fourth energy level, fifth energy level, sixth energy level, and seventh energy level. They'll all have s orbitals. An s orbital, as you can see, is basically a sphere. As you can see here, you think of the nucleus kind of here. There's the x, y, and z coordinate plane here, and kind of there. And again, the higher probability kind of in the middle there, near the node, which is sometimes referred to there where the nucleus is, as where you would have a high probability of finding an electron. They're basically all a sphere. They do increase in size as you go from, say, the first energy level to the second to the third to accommodate all the electrons that are present. When we talk about s orbitals, there is only one type of s orbital, no matter what energy level you're at. And that means that on every energy level, you could think of it as like a 1s orbital. It could only hold a maximum here of 2 electrons. So if you fill up the s orbital on the first energy level, that means that you put 2 electrons in it. Again, each of those arrows are going to represent an electron here. If you go to the second one, you put 2 in there, that's going to be filled. Third one is going to be filled as well. Now, the next set of orbitals actually do not start until we hit, oops, let me come back here, until we hit actually the second energy level. So on the first energy level, as we were talking about, we have only a 1s orbital. When we go to the second energy level, there's a 2s orbital. And this is where we start to see what is referred to as the 2p orbitals. Now, the 2p orbitals, there's actually 3 different types of p orbitals. There's a px orbital, a py orbital, and a pz orbital. As we'll see on the next slide there, they're basically like figure 8s type looking teardrops, are sometimes described as. And again, each of these can hold a maximum of 2 electrons. So if we take this entire thing out over here on that n equals 2 level, we have our 2s and 1, 2, and 3. Each of these lines will represent a different 2p orbital. That's the 2px, 2py, 2pz orbital. Each one could hold a maximum of 2 electrons. So individually, the x, y, and z, which as we will see, let's just take a look at it here. I think on this slide, there we go. X, Y, and Z means that they are at, you can think of the nucleus here, that's sort of where the no amplitude. And again, these are places where high probability of finding electrons are, around here and here, near where that nucleus would be. This is the X, Y, and Z, is sort of their orientation in 3-dimensional space. So we have one orbital on the X, one on the Y, and one on the Z here. So what does that mean? It means that if you take all 3 of these individual p orbitals that are found on the second energy level, this is what is sometimes referred to as the 2p subshell, and some books will call it a sub-level. So when we talk about the 2p subshell, for example, it could hold a maximum of 6 electrons, 2 in each of the p orbitals. So p subshell can hold a max of 6 electrons. You do not have to necessarily fill up the p subshell completely with electrons, but if you did, you would have put in there 6 electrons, and we're going to talk about how to do that shortly. But a maximum of 6 to fill the subshell. Individually, though, the px, the py, and the pz orbital could only hold 2 electrons. So this orbital here could hold a maximum of 2 electrons. This orbital here could hold a maximum of 2 electrons. This orbital here could hold a maximum of 2 electrons, which means 6 electrons max in terms of our subshell, which is, once again, all 3 of these orbitals together on the same energy level. So p subshells do not start, or p orbitals do not start until you get to the second energy level. On the first energy level, we have s orbitals. On the second energy level, we still have s orbitals, and that's where we start to see p start to develop. And when we get to the next sort of energy level, that's where we start to see the next type of orbitals, which are d orbitals. So on the first energy level, which is the lowest, we only have s orbitals, which is referred to as a 1s because it's on the first energy level. Second energy level, we still have an s orbital, but it's called a 2s because it's on the second energy level. Also where we start to see, as we just saw there, our 2p subshell. When we get to the third energy level, we also have s orbitals. We also will have p orbitals, which you might guess are called a 3p subshell. 3 meaning that's on the third energy level, p means that p subshell. And this is where we start to see the d orbitals appear. And there's actually 5 different d orbitals. So as you can see here, 1, 2, 3, 4, and 5. They sort of look like 2 p orbitals together. One kind of looks like a p orbital with a donut in the middle there, the fourth one, but basically kind of 2 p orbitals together. Now, because there are, again, 5 different d orbitals here on the third energy level, this is what is sometimes referred to as the 3d subshell or sublevel. And once again, each of these individual d orbitals can hold 2 electrons. So it's 2 electrons for that one, 2 electrons for that guy, 2 electrons for that guy, 2 electrons for that guy, and 2 electrons for that guy. So if I add all that up, I am maxing out my d subshell with 10 electrons, basically 2 in each of these. So d orbitals do not appear until the third energy level, and then they are there on the third, fourth, fifth, and sixth energy level is where you find d orbitals. Now, there's one more set of orbitals that actually appear on the fourth energy level. So when you get to the fourth energy level, that is where f orbitals actually appear. And there's actually 7 different types of f orbitals. So if we kind of draw it on our first energy level, once again, all we have is the s orbital. Second energy level, we got the s orbital. And again, that is where we first start to see our p subshells occur, our p orbitals. Third energy level, still have the s, still have the p. And then that is where we start to see our d orbitals appear. Now we get to the fourth energy level, still have an s, which is known as a 4s. That is where we have a p as well, which is a 4p subshell. Still have a d, so 4d. And this is where we first start to see the appearance of our f subshell, 4, 5, 6, and 7. And this is our 4f. Once again, all these together is our 4f subshell, our sublevel. And as you can imagine, if there are 7 different orbitals and each individual orbital can hold 2 electrons, as 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, and 14. Again, if each of these lines represents a different f orbital, you can max out the f orbitals, or the f orbital, the f subshell, with 14 electrons maximum. Once again, you don't have to fill it all the way up with 14, but 14 will max out all of the f subshell. So these are, again, the s, the p, the d, and the f are all places in the atom theoretically where electrons are housed. Again, this is moving away from Bohr's model of orbits to these probability maps, which are known as atomic orbitals, where there's high probabilities of finding electrons. And again, we do not know exactly how they're traveling. We don't know exactly where they're located, But what we do know is that they are not moving in pretty little circles and orbits around the nucleus. They're moving randomly about the nucleus. So speaking of the energy of these orbitals, and a couple of things here, as I mentioned before, a grouping of orbitals on a particular energy level are referred to as a subshell or sublevel. If you took the entire orbitals on a particular energy level, as this would be n equals 1, n equals 2, n equals 3, n equals 4, this is what would be known as either a shell or a level. So for example, if I ask these three questions, how many electrons to max out the following: a 3p subshell, the n equals 2 level, our shell, and a 4p orbital. So why don't you take a second and make sure you understand sort of the terminology that is sometimes used here with these type of things. Answer those three questions. I want to know how many maximum electrons to fill a 3p subshell or sublevel, the n equals 2 level or shell, and a 4p orbital. So take a moment and see what you come up with here. Okay, let's take a look. So here's the deal. We're going to start with the 3p subshell. So 3p subshell is all of these guys together. So that is 1, 2, 3, 4, 5, and 6. The answer would be 6 electrons if you filled it up completely. The n equals 2 level or shell, that is, as I previously boxed, everybody found on the n equals 2 level. That consists of the 2s orbital, also consists of the 2p subshell. So that is a grand total of 8 electrons. 1, 2, 3, 4, 5, 6, 7, and 8. Now, lastly, the 4p orbital. Now, if you said this answer for 4p orbital, 6, incorrect. 4p orbital, remember that any individual orbital, could be this guy, could be that one, could be that one. Any individual orbital can only hold a maximum of 2 electrons. It's kind of a trick question sometimes they're asked. Any individual orbital can only hold 2 electrons. What is the difference between that? If the question was how many electrons for the 4p subshell, now the 4p subshell would be everybody together, which would then get us the 6. So that is the difference between those two questions. A 4p orbital can just be one of those, could be the px, the py, or the pz orbital, or a 4p subshell, it's all of them together. So that's the slight difference there. So 4p orbital, 2. You took the entire subshell, 6. So those are some terminologies that sometimes people get a little confused upon. Just wanted to clarify that. Also, in addition, you may not want to have to draw all this out with all the arrows and stuff like that. So there is a quick way if you just want to know the maximum number of electrons on a shell or level. You could just use this formula, 2n squared. N is the principal quantum number. You square it and then you times it by 2. So for example, we did 2 a second ago. 2 squared is 4. 4 times 2 is 8. And that is how many electrons there was. Say you want to do the third energy level. 3 squared times 2. 3 squared is 9. 9 times 2 is 18 electrons. So if we went to the third energy level, that is 1, 2, 4, 6, 8, 10, 12, 13, 14, and 15. That's not how they actually go in. And I counted wrong there, so I'm going to do it again there. 2, 4, 6, 8, 10, 12, 14, 16, and 18. think 18, not 15 there. There you go. And that's how you can do it. So you can use that formula there to figure out the maximum number of electrons on a particular level or shell. You square the principal quantum number, which is the n number, and then you times it by 2, and that'll tell you how many electrons on the entire energy level in every orbital if you max every orbital on that energy level out. All right. Actually, I think to not make this lecture super long, this is probably a good stopping point. The next lecture will continue on from this point, and we will cover electron configuration, how to write electron configuration, where all the electrons are in an atom, and we'll also hit about electron configuration and ions as well. So for now, we will call it done here for Chapter 10, Part 1. And of course, we will see you for Chapter 10, Part 2, coming up, the conclusion of where did my electrons go, I suppose. All right, have a good one. We'll see you in a bit.
Hello there, and I hope you've enjoyed part 1 of this lecture. We should obviously finish with a good, appropriate chapter joke. Here it comes. Sodium said to potassium, "Oh no, I've lost my electron." To which potassium replied, "Oh no, are you positive?"